Well, welcome to this session, and we shall start. It's a little late, so we will try to keep on time. First speaker today for this session is Dr. Jean-Pierre Charles Revol. I think everybody already knows who he is, but just to remind, Dr. Revol is one of the founding members of the International Thorium Energy Committee and became its first president in 2012, and he will give us his presentation on a first ADS demonstrator. Dr. Revol.
So just a small comment. This talk was moved to the plenary session, so at one point I was asked to move the talk to the plenary session, but still give the talk in this session. So there will be a little bit of repetition, but not too much. I will take this opportunity to say a few things I did not have time to say in the session. I already mentioned that iThEC is an international association to promote innovation, more specifically in the development of thorium nuclear technologies. And I would like to concentrate on the next step, which is a first concrete step towards exploiting thorium. That is, we would like to couple for the first time a proton accelerator to a subcritical core of significant power. All right, so I just want to remind you that actually one of the strongest motivation for using thorium is that thorium is a sustainable source of energy on the human time scale. That was, I'm not the only one saying that in this conference, but Carlo Rubbia made the point already a number of years ago. And what's interesting with thorium is the thorium, the energy intensity to generate 1 gigawatt electric during 1 year. It takes 2.5 million tons of coal and only 1 ton of thorium. So in view of the dramatic effect of burning fossil fuel on pollution and also on global warming, I think it is in itself a very strong incentive to try and use thorium. And in fact, it's amazing to note that if you burn actually 2.5 tons of coal, you collect at the same time 13 tons of thorium, and you could produce 13 times more energy with the thorium in the ashes of the coal than you produce with the coal itself. Thank you. So the other extremely interesting aspect of thorium is that it minimizes the TRU production, it minimizes waste production, and if you associate thorium to a fast neutron flux and do recycling, then you can make the waste inventory as small as you want. And in fact, I have here a little insert that shows an experiment that was done at the French CEA called CAPRA, where they measured as a function of concentration of plutonium, the rate at which you can destroy plutonium, and you can see that the breeding equilibrium is about 15%. Now, if you put plutonium in a thorium environment, it turns out that the breeding concentration is 10 to the minus 4, 10 to the minus 5. So it's easy to understand that as soon as you put some plutonium with thorium, it burns because you're always in this mode above the concentration of equilibrium. If you are below, you breed. If you're above, you destroy. So with thorium, you are far above, and this is why an ADS with thorium will burn extremely efficiently those things. In fact, if you look at the rate at which you destroy, for example, plutonium, you can destroy the plutonium in an ADS, you find out that you have to go to concentration of order 50 or 60% of plutonium in a fast critical reactor like was simulated in CAPRA. And then you realize that those things cannot work with such a high concentration for practical and safety reasons. So it's true that you can destroy a certain number of things in fast critical reactor, but it's difficult to destroy things at a very high rate, at least compared to ADS. So ADS, I already showed that, but it's a beam that goes to a target, lead or uranium, heavy metal that produces neutrons, and then you arrange the system to have this source neutron interact with the core where you have fission. So you have two type of things. This is the distribution of energy of here the fission neutron. It's average about 1 MeV, and here for a proton beam of 1 GeV you get this type of profile of the spallation neutron. Is not so different from the fission neutron on average, but it has a high energy tail, which is more important. And in fact, this tail is quite interesting because it's high energy. You promote NXN reactions, and that means that there is multiplication in the tail. And of course, when you switch off this multiplication, and it has extremely interesting implication for an ADS. I will come back to that in a moment. So you use an accelerator as a source of neutrons, and then you have a core with this phenomena. And if you combine, because thorium by itself is not intrinsically safe, but you combine the fact that you want to make a subcritical system, and you still have to deal with removing the heat from the system. If you use passive processes, both for heat removal and for safety, you can use air vacs to evaluate, which is an air-cooled chimney around the system that was developed for advanced fast reactor in the US. Then if you combine all these, it is certainly possible to make a system which is inherently safe. So what the accelerator does for you is that it allows you to, this is the, let's say, the breeding quality as a function of neutron energy. And you can see U233 compared to plutonium-239. Clearly, U233 is a better thermal breeder. However, for the reasons I mentioned already, we want to use a fast neutron flux because we want to fission all the TRUs, and therefore we want to use it in a place where it's the other way around. Plutonium is doing better, and that is one of the reasons you need the accelerator to produce a few more neutrons to make a good breeder out of U233. So I mean, this is one thing. Both you allow with the accelerator to work in this regime, and in turn it allows you to destroy TRUs. Another comment I want to make on ADS is that it's probably complementary to various nuclear scenarios. We are not talking about replacing reactors with ADS, but complementing them. For example, if you are one strata type of system with UPU, then the ADS could be your burner for minor actinides. Or if you use the ADS to burn TRU, then you can use it as a breeder for U233. You put your nuclear waste as fuel, and you generate U233. So we will see what people want to do. And a last comment I would like to make, the fact that you have an accelerator, you have to understand that the multiplication factor in the system does not depend on the accelerator intensity, it depends on other things. So you can modulate the power out by modulating the power of the beam. And in fact, I think green people should realize that since they are dealing with very highly fluctuating renewable energies, solar or wind, ADS might be an ideal thing to complement that. And whenever there is no sun or no wind, then you run the accelerator at a higher intensity. The theory of subcritical system is really fun, and I invite all the students to study this. You can do it analytically if you want to get some insight into the system. Of course, if you want to really simulate a real system, you have to go to a Monte Carlo method. But this is nice. You can do something. So this equation is the same, very similar to what you have for critical system, except that there is an additional source term, which is the neutron source brought by the accelerator. And then I want to come back to what I said about the high energy tail of spallation neutron. They give you an extra term in the multiplication coefficient, and you can see that as soon as you switch off the system, this term disappears, and by definition, what we call now K source, which is the multiplication factor when the accelerator is on, is larger than the effective K of the system once you switch off the accelerator. So if you run at K of 0.98, you stop the accelerator, immediately you go to a lower K value, and of course this is very good because you want to be as far away as possible from criticality. So the physics of ADS is completely known. There has been 2 pioneering experiments at CERN, at the CERN PS, measuring in detail in a subcritical system with a K of 0.9. That was uranium, and it was a thermal system with there was water, and detailed measurements were made. And then the ThEC experiment used 400 tons of pure lead to study the phenomenology of neutrons in lead. So all this is very well known. And in fact, what has been learned is that as far as beam energy is concerned, you have an optimum energy between 800 and MeV and 1,000 MeV. So you don't need the energy of the LHC at 7,000 GeV to make the best out of this technology. Of the order 1 GeV or even lower is already optimum. So once you validate simulation, you can look at how well you can destroy actinide. You know, the TRU destruction rate normalized to terawatt thermal hour is 36 kilos in the Rubia system, and for comparison, a PWR producing the same amount of energy produces 14 kilos. This is the net production, the net destruction. That means that's the difference between what is generated and what is burned. So you really destroy TRUs for the reason I explained before. And well, there are other calculations that have been done. Yassine Kadi has simulated a slightly different system optimized to destroy plutonium, and in fact, you can go to 42, 43 kilograms of plutonium destroyed in this system, to be compared to 11 kilograms produced in the PWR. But the major point you can see here, this is the radiotoxicity versus time, and this is the typical PWR waste in an open system. Actually, if you would run MOX, it would be even higher. And if you recycle, and depending on your recycling efficiency, then you can go to a level which is lower than the radiotoxicity of the coal ashes for the coal that would have produced the same amount of energy. And you know, I was told that you can achieve reprocessing efficiencies of 99.98% these days. So you see that that gives you almost 4 orders of magnitude reduction of the inventory. So what do we have today? We have beams of power in the megawatt regime. I mean, here is the PSI cyclotron, 1.3 megawatt at 0.6 GeV. We have SNS, the American spallation neutron source, that also runs above 1 megawatt of power with 1 GeV. So we already have systems which provide significant beam power. And of course, you need about 10 times more beam power if you want to realize one of these ultimate system, like the one designed by Aker Solution in collaboration with Rubia for 15 megawatt of power. But before you go to such achieved project of a large scale, you need to do a little bit of test and demonstration. This has to be done and has not been done yet. It has to be done with a significant power. The FIT experiment that I've shown to you was already an ADS, but the power was 1 watt. And of course, if you use particle physics detection techniques, 1 watt is a lot of power, and you can do a lot of great measurements, but this is not enough to understand how industrial system will work. There were many attempts in the past at having a prototype. In fact, one of the most achieved attempt was a system designed by Ansaldo in Italy. Ansaldo is an industry involved in nuclear systems, and it's also one of the companies that build the LHC magnets for CERN. And that was proposed to the European Commission in 1999. And of course, they asked nuclear industry what they thought about that, and it was unfortunately turned down. You can imagine that if that thing had been approved at that time, we would know a lot more about ADS today than we know, actually. So the point is that no ADS attempt so far has exceeded 1 kilowatt, and you need at least 1 megawatt to learn what you want to learn to prepare for the industrial era. See, here is a summary of all the ADS. It might not be totally complete, but the main points are here. The very first one, FIT at 1 watt. And here there is Mira that I will discuss in a moment, and the design. In fact, there is now a very aggressive program in China where it's a 4-phase program that started in 2011 and is scheduled to reach the GV and beyond in 2031. It's promoted by one of the vice presidents of the Chinese Academy of Science, Professor Wenlong Zhan, and it is a very ambitious project, and maybe we'll hear about that at this conference. And then there is something that iThEC got interested in. There is a proposal at ThEC, at the INR, Institute of Nuclear Research. It's near Moscow at ThEC. And this is actually an interesting possibility that I'm going to discuss in a moment. This is Mira. It's a system of 600 MeV beam for 4 milliamp of protons, so it's 2.4 megawatt of beam, and to reach a power between 60 and 100 megawatt. This is a real interesting design which is prepared for in Belgium, and this would be the most natural next step, and there is a strong support from the Belgian government. However, unfortunately, it's only partially funded. There is no thorium on the program, and we have learned that after some years of operation as an ADS, people will remove the accelerator and make it a critical system to do other type of studies. So unfortunately, Mira will take a long time. So what can we do today if we simply use the accelerators that we have? You can see here, this is beam power versus K source. Okay, and you can see here curves of constant thermal power. So this is the thermal power of the energy amplifier of Rubia, and you can see that if you run as he proposes at K of 0.98, you need 12.5 megawatt of beam current. So we are not there yet, but if we use the type of beam that we know how to do today, which is the beam running at SNS, the beam that Mira wants to do, you can see that you can reach easily the 100 to 300 megawatt type of system. So today we could make an ADS that works because we know how to make the spallation source, and we know how to make the beam, and this is for a range of K source which is reasonable. It does not exceed the 0.98. Of course, you could even go a little bit higher and get even higher power. So at ThEC, there is a proposal that was presented by Stanislav Sidorkin at ThEC15, so the previous conference, of an ADS demonstration, and iThEC recognized that it could be a realistic possibility of having a first ADS demonstrator, so we looked into it carefully. This is the delegation of ADS. It's a set of experts. This gentleman is an accelerator expert from CERN. This is nuclear safety experts in Switzerland. This is Yassine Kadi, which is very well known in the field. He's at both the culture of nuclear engineering and particle physicist because he worked with Rubia. And this is Sidorkin. So we evaluated the system. You can see the LINAC, it's 600 meters long. It's an impressive object, but the big merit of this is that it exists. You see here another area with some accelerating cavities and so forth. And the tour was given here by the Deputy Director, Alexander Feshenko. And we reviewed what has to be done. This accelerator is actually running, but not at the optimum capacity for various reasons. And then there are two spallation sources. This one is in operation, and there is another one that is free and could be used as the place for ADS. Here it is. We were there, and it would be under this cover here. You know, both the beam exists and the spallation source, and what remains to be done is to design the core. So the iThEC delegation was there and concluded that the ADS at ThEC can fulfill the requirement for a useful ADS demonstrator. The facility, once commissioned, actually would become a real facility, not only an ADS test. We can study material science, nuclear physics, nuclear technologies, liquid metal cooling, fuel composition, processing, instrumentation and control, computer simulation technique, and so forth. I mean, it's a real facility that could have could draw interest from other areas. So last week, actually, iThEC decided to proceed to the next step, which is to implement a very detailed feasibility study. What do we want to learn from that? We want first to demonstrate ADS as a substantial power, and we determined that the minimum power is 1 megawatt, and that can be done. We want to learn how to operate an ADS of such power. In particular, you have to define and demonstrate the safety features of an ADS, because it's a system which is quite different from a critical system. And we want to use everything that we learned here to prepare the design of a prototype of an energy-producing unit of industrial power. And I've told you today that already a few hundred megawatt is achievable with today's technology. And we also want to demonstrate the possibility of destroying minor actinide. So this is the characteristics of the accelerator. Initially, that accelerator was designed for 600 MeV and half a milliamp of current, but never achieved that. And actually, today it's not even achieving this level of performance, just because some of the equipment has to be replaced, in particular some of the klystrons. So what can be done with that system? First, the beam energy, at least initially, will be 250 to 300 MeV, but it could reach one day 550 MeV. So the beam power will be 25 to 75 kilowatt, and it could certainly go higher. It's a pulse beam, so this is very interesting to do physics measurement. As you know, that you can interrupt the neutron production and then measure the evolution between pulses. So it only lacks spare parts, and that's the only reason why this is not achieved. But depending on the investment that is made, you can go from here to there eventually. The spallation source exists, the design of the core exists, but it should be further optimized. And clearly, the design and construction of the core requires collaboration with Rosatom, which is the ministry in Russia that deals with the nuclear aspect. Of course, the ancillaries and supporting equipment should be submitted to a thorough safety review by the Russian safety authorities. And wherever needed, it should be upgraded. However, it's also clear that the presence of significant amount of nuclear fuel may imply the need for a new containment structure, but it's not in itself a showstopper. So this is what you can do with 25 kilowatt at 247 MeV. I took these two numbers because that's the minimum guaranteed from the start. And of course, we will do better, but already with that, you see as a function of K, the thermal power you produce. So we want to reach the 1 megawatt level, and therefore we need a K of 0.972, and this is already reachable with this. Of course, most of the time we'll run at least twice the power and probably even higher, up to 75 kilowatt. So then you can reach the multi-megawatt level, at least 2 to 3, and perhaps one day even better, either by increasing the beam power or running at a higher K. So what happens at ThEC is here you have the same plot with beam power versus K source, and you see lines of constant power, but this is at a beam energy now of 250 MeV. The energy amplifier of Rubia runs with the 1 GeV beam, so the curves are slightly different, but you can see the range of K that you need to go from 1 to 3 megawatt of power. So you see that it's very reasonable. You don't need to go above 0.975 or something like that. So that certainly can be achieved. So there will be the first phase will be a campaign of physics measurement. You have to characterize the new spectrum. The flux density mapping will be done. You have to study the neutron source dynamics, the effect of K source, the difference between K source and K effective that I mentioned, and this is where a pulse beam is really interesting. The delayed neutron fraction, the fuel evolution, and so forth. So it will be actually very exciting to do physics with this system. So my conclusion is that the ThEC project would be the first ADS of significant power, and it is clearly a long-awaited and necessary step in view of the design of an industrial system. So a power of 1 to 3 megawatt is feasible with what we have. Perhaps one day we can even push it to 5 megawatt, and it is more than sufficient to fulfill the iThEC program and can allow many more measurements of general interest. So it will not be only an ADS system, it will constitute a facility. If somebody wants to test some property of a specific thorium fuel, they will get here a fast neutron spectrum that they can use. So the project costs only 5% of the cost of Mira and can be achieved in 5 years. And I think that's one of the reasons why we believe it's actually feasible. And collaborators are welcome. Thank you very much.
Thank you, Dr. Revol. That was very enlightening. Bit of time here, so we can take about 2 or 3 questions. It's open to the floor. There.
I am not sure whether it is the proper forum for this question, sir. Actually, you have already mentioned that collaborators are welcome. I was thinking about that CERN experiment which we are doing. I think that consortium kind, I think many countries are involved, that they are contributing. In similar way, whether we can go for this ADS and the thorium, power from thorium, whether it is possible. Just I was thinking, if you can respond to that, sir.
Well, I don't know exactly how to respond to this, but I want to say that, you know, innovation comes in doing new things, and this has not been done, and I think clearly it has to be done. I mean, I don't think anybody knows how the first real industrial ADS system will look like, but we want to do something. I think I'm sick and tired of going to ThEC thorium conferences. We always say the same thing, and there is nothing new. So what we are trying to do now is to do something new so that at the next ThEC conference we can really talk about something new. We won't have yet in 2 years this thing up and running, but I hope we'll be well on the way to achieving that. And so, you know, new ideas come by doing new things, and this is one new thing which I think is realistic, and this is what we want to do.
Excuse me, it was a good presentation. There are different concepts of the reactor which will be coupled with the ADS. So some of the concepts at the middle, at the center it is fast spectrum, at the peripheries it is thermal reactor, and the whole spectrum like a fast reactor plus a thermal reactor. Those kind of designs were also considered. But I'd like to ask you, your presentation also covered that if it is a burner, waste burner optimized design, and if it is a thorium breeder optimized design, is there any major difference?
Well, there is no basic difference. You know, I think, I hope I convinced you that you need a fast neutron spectrum to be a good burner. And therefore, if you have a fast neutron flux, you can explore the property of the system as a burner. You know, the limitation on the burner will not come from the design of the neutron flux. It will come on how difficult it is to make the fuel, for example, and things like that. So I think
waste burner, actinides burner, like.
Yes, that's
okay.
what we're talking about, actinide burner. You know, that's about all you can burn is actinide, because when we say burn, actually we mean fissioning, right?
Yes. Yeah. And this, can you comment on the windows? Like it is a window, how these windows are designed for Accelerator?
Well, the window already exists because there is already a spallation source. That's
so a windowless design or a window design is better? Like?
The spallation source exists. Like it's like an. Also, I showed you that SNS already exists. So we already know how to bring the beam on the target and produce neutrons.
Fine. Thank you.
Okay, I think, yeah, this is the last question.
Okay.
Thank you.
Sir, I was just interested in knowing how would you map the fluxes? You mentioned that you were going to map the fluxes in one of your slides. So basically, what sort of flux mapping techniques are you going to use in this?
Sorry, can you repeat the question?
You mentioned that you will be using flux. You will be mapping the fluxes in one of your slides in the
Yes.
experiments you proposed.
Yes.
So I would like to know what kind of. There are different mapping technologies which are available, right? So what kind of mapping like you are going to use in that? Like
I think we probably use the same technique we use in the ThEC experiment. You know, if you want to measure neutron flux over a large neutron energy range, you need to combine several techniques. So for the fast neutron, you probably use helium-3 ionization chambers.
But they'll be placed outside the core, right? Because it's a fast system, so.
No, well, we have to put detectors at various places inside the core. You have to measure, you know, the neutrons where they are. So there will be various techniques for doing that. It's standard techniques. And as I said, you know, to cover a broad neutron energy range, you have to combine different techniques. You can do time measurements. You can do ionization for the very fast neutrons and other techniques for thermal neutrons and so forth. But in the end, we want to know the neutron flux with the best possible precision. In ThEC, we achieved a precision of 15% on the magnitude of the neutron flux over 8 orders of magnitude in energy of the neutrons.
Okay, sir. We'll discuss it later. Thank you.
All right, well, thank you very much. I think we're a bit out of time. Let's thank Dr. Revol for that very enlightening presentation.